In this video, we're going to be talking about complex zeros and the fundamental theorem of algebra. So let's start with the formal definition of the fundamental theorem of algebra. So what you see on the screen in front of you essentially says that for any complex polynomial function, where that is a function that has a degree of 1 or more, it's going to have at least one complex zero or root. Complex coefficients, at least one complex root. Sometimes that root is repeated, but that's how it goes with the roots of a polynomial function. Going along with the fundamental theorem of algebra is the conjugate pair theorem. Now remember, a complex number can be expressed in a plus bi, where a is the real part and the bi is the imaginary part. So in order to eliminate that middle term when we FOIL out, if you remember, we use the conjugate. So if a plus bi is a factor of a polynomial function, then a minus bi is also a factor of the same function. So let's focus on an example where we're going to actually use the fundamental theorem of algebra and the conjugate pair theorem. So let's find a polynomial function, which means that we're going to write the function with a degree 4 and zeros 1, 1, and negative 4 plus I. Right off the bat, I notice that I have repeated real roots right here, and I have a complex root. Now, there's only 3 listed here, so that means I'm missing my 4th root because it has a degree of 4. And what I know from the conjugate pair theorem, if negative 4 plus I is a root, negative 4 minus I must also be a root as well. So using the definition of the fundamental theorem of algebra, I'm going to set up my basic polynomial function, where there's going to be some coefficient on the outside, a, which in a moment we'll deal with, and then I'm going to plug in my zeros. So because these turn out to be positive, I know it's going to be minus 1 within the parentheses. Do the same thing here, except now I'm actually subtracting my first complex root here and my second one that I found out just a moment ago. And what I'm actually going to do is I'm going to assume that a is 1 so that I don't really have to deal with multiplying out by a constant to the entire function that I have here with degree 4. So what I'm going to do is I'm going to FOIL these two, and I'm going to FOIL these two, and then I'm going to distribute like crazy, and I'll show you what that looks like when I simplify it down. So from expanding everything out and doing a lot of arithmetic, I end up with f of x equals x to the 4th plus 6x cubed plus 2x squared minus 26x plus 17. And looking at the graph of this function, I see that the only real root that it has is at 1. And we know from the work that we just did that it's going to have a repeated real root at x equals 1. So now let's check out another example where we're actually asked to work backwards to find the complex zeros of a function that we're given. So the first thing that I do is I look at the leading term there, and I see it's 3x to the 4th. So that is a degree 4 polynomial, so I know that it has at most 4 zeros. And now I'm going to use the rational zero theorem, the one with p over q, where our 18 is p and 3 is our q, and I will list out all the possible rational zeros and then divide from there. So when I work out that entire list, I'm left with all of these possible rational zeros. So what I do next is I graph the function, and I try to see if anything on that list is on the graph. So what I notice here is that this function actually crosses the x-axis twice. Once at x equals negative 2, and another time at some fractional value, which is probably 1/3 or 2/3, judging by the list that we just made. So the next step in this process is to take our root of x equals negative 2, turn that into x plus 2 here before it gets factored out or set equal to 0, and I'm going to use that and divide it into my entire function using synthetic division. So I'm going to fast forward through that right now. So I know that I did this correctly because I have a 0 remainder down here. And what I'm left with is another function up here. And I can factor this. Unfortunately, it's not a quadratic, but it is a cubic, and I'm going to take that another step further and factor that out to find the other roots of this function. All right, so I've written each piece in different colors, and I'm going to factor out the common factor of 3x cubed minus x squared, which is x squared, and I get a 3x minus 1. And then over here, I'm going to factor out a positive 9 and get a 3x minus 1. And my goal is to get the same thing in the parentheses so that I can take it a step further and combine this to be x squared plus 9. And then I just bring those together because they've been factored out as one term. So I'm going to set them each equal to 0 and solve. So when I solve these two things, over here on the right, I get my 1/3, which was that root on the positive side of the x-axis, which we weren't really sure if that was 1/3 or 2/3. Turns out it's 1/3. And then on the left here, I have x squared plus 9 equals 0. And what that turns out to be is positive negative 3i. So those are my other two roots, but they happen to be complex or imaginary. So in total, we say that our roots are x equals negative 3i, positive 3i, negative 2, and 1/3. So if we are asked to take those roots one step further and actually write the function in factored form, we're going to take our roots here, and I'll show you the two steps that I use to factor this out. So I know what my roots are, and I'm going to write it in my factored form, which looks like x plus 3i, x minus 3i, x plus 2, and I'm going to take it back to our last page where it said 3x minus 1 equals 0, because that's what I originally got this 1/3 from, and I'll show you why that's important for our a value. So I can actually factor out a 3 from here in order to get that to be 1/3. So if I divided this term by 3, my new function, if I bring the 3 to the front, will look almost identical, but this is how it's completely factored. And that works because if I were to distribute that 3 back to this term, it'd end up with our 3x minus 1. That's going to do it for this video. Thanks for watching.